Hello and welcome back. In this video, I'm going to show you how can we use an Unscented Kalman filter to estimate the states, hidden states, and identify, for example, the hidden parameters of these three-story building. Usually, we model this three-story building with damped mass spring system, which all of us know that how to write the mathematical equation of this system from vibration or vibration books. In any standard vibration books, you can find the mathematical equation describe the behavior of this 3 degree of freedom system. And I put my Ph.D. thesis link in the description. You can go because over there I talked about it as well. The goal is to see how can we estimate the stiffness damping, assuming we know the mass and the acceleration of vibration on some specific floors, and some specific in other floors the measurement is missing. For example, we assume we place this three-story building on a shake table and excite the shake table using a recorded ambient vibration. It could be earthquake, history, or any kind of ambient vibration. And after that, we assume that we install two different accelerometers in floor 1 and floor 3 and measure the acceleration of vibration. And the question is, okay, we have the excitation, we have the vibration response, and what I'm looking for is K1, K2, K3, C1, C2, C3, displacement at each floor, and velocity of vibration at each floor. Then I'm going to write down the mathematical equation, the state space model, and the state vector, and see how can the Unscented Kalman filter can be used to estimate the parameter of interest, technically. For this kind of equation, if I'm going to write the equation for you to have the clue what I'm talking about, the equation, I don't want to prove the equation where the equation come from. As I said, you can find them in any standard vibration. The equation will be M1 x double dot 1 plus K1 K2 x1 minus K2 x2 plus okay, what I'm going to do, because this is the recorded, for example, for this case study, I was using the history of an earthquake, El Centro, the earthquake history. Then, because this is acceleration of the earthquake, then I need to multiply it by the mass, which I call it M1, which is the mass of the floor 1, times Ag, which is the history of the earthquake. Okay, this is the equation for the first floor. Then I forgot to say, for example, here, if I go up, this is K1 and C1. It goes here, C2 and K2, and here will be K3 and C3. And I call this one I'm going to write it here, Ag, for example. Okay, then you see, we assume we know the mass. We are looking for K1, K2, K3, C1, C2, C3. This is the equation for the first degrees of freedom. I'm going to hide the vibration. And for second degrees of freedom, it will be M2 x double dot 2 plus K3 x2 minus K2 x1 minus K3 x3 plus C2 plus C3 x dot 2 minus C2 x dot 2 minus C3 x dot 3 equal to M2 Ag. And for the third degree of freedom, it will be M3 x double dot 3 plus C3 x dot 3 minus C3 x dot 2 plus K3 x3 minus K3 x2 equal to M3 Ag. This is the governing equation, the ODE equation describing the physics of the system. Then the first step to be able to use Unscented Kalman filter is to write the equation in a state space form. Then to write the equation in the state space form, we need to define the state vector. In this case, I assume my state vector x okay, is equal to x1, x2, x3, start 1, start 2, start 3. Okay, I'm looking for these 6 states, and also I'm looking for K1, K2, K3, C1, C2, and C3. These are the states and parameters I'm looking for to identify. Then I define them as Q1, Q2, eight, Q9, 10. Okay, we have 12 states to be estimated or identified, and this is a joint state parameter system identification problem. To write the equations in the state space form, then we say, for example, Q dot 1 is equal to Q4, Q dot 2 is equal to Q5, Q dot 3 is equal to Q6. Yes. Then to find the Q dot 4, Q dot 4 is equal to x double dot 1, which we have to use this equation. Okay. Then what I'm going to do, I'm going to write this equation based on as a function of Q. I'm going to write all the parameters I'm interested to identify and estimate. I'm going to write the Q dot 4 as a function of the different Qs I have in this state vector. Okay, for example, for x double dot 1, it will be, because we have M1 here, I divide the whole equation by M1, M1 AG. It will be minus K1 is equal to Q7. Q7 plus Q8 times X1. X1 is Q1. Yes. Then this is positive, goes to the other side, it will be negative. This will be positive plus, I'm going to hide this one as well, plus K2, which will be Q8. X2 will be Q2 plus Q10 plus Q11 times Q4 minus, this will be negative. If it goes to the other side, this will be positive. Will be Q10 times Q5 equal 10. That's it. Okay. Then what I did, I wrote my Q dot 4 based on this equation, which is a fine. I substitute everything based on the Q you see here. Then I do the same thing for Q dot 5 and Q dot 6. Okay. Then you just need to replace these two Q, substitute Q as in these two equations and write them here. And okay, so far we wrote everything for Q dot 1, Q dot 2, Q dot 3, 4, 5, 6. What remains here is, I'm gonna write, for example, Q dot 7, for example, Q7 was K, okay? And because we assume Q stiffness is fixed, then its Q dot will be 0. The same as for Q dot 8, Q dot 9. Yes. As you see, because we assume that the stiffness and damping values are constant, the derivative is equal to 0. Then right now, what I did, I wrote the equation of motion of the system. I defined my state space, my state vector, which includes all the quantities of interest, states, and parameters. I wrote my transition function in a continuous domain. You see, I didn't write the equation in a matrix form. Everything is based on the function. I wrote here for the first equation. For the second and third one, you can easily do it. And feel free to ask me in the comments if you cannot handle it. And you can find the details equation in my papers as well. I put the paper in the description. Now, I'm gonna write the measurement function for you. Just showed you how to write the transition function in the continuous domain. Now I'm going to show you how to write the measurement function in the continuous domain. As I told you, we have the acceleration of the vibration in floor 1 and floor 3. Then the measurement function, y hat, will be x double dot 1, x double dot 3. Then write it down. We use the first equation and third equation and write them based on the state vector we have. Then it will be 1 over m1 ag minus. Then I write the equation based on my state vector, my state vector q's. It will be q7 plus q8 q1 plus Q8, Q2 minus Q10 plus Q11, Q4 plus Q11, Q5. Yes, this is my equation for the measurement function for my first measured acceleration of vibration. Then my third one will be M3 AG minus, I will use this equation, which will be minus Q12 Q6 plus Q12 Q5 minus Q9, I'm sorry, Q9, X3 will be Q3, plus Q9, Q2. Yes, this is my whole, okay, this is my measurement function, and I showed you how to write the transition function in the previous, in a couple of seconds ago. Okay, then right now, what we did so far, we wrote the measurement, the transition function in a continuous domain. We wrote the measurement function again in the continuous domain. What we have to do right now, we have to translate or convert this equation in a continuous domain into discrete domain, and to be able to use it in the Kalman filter, in the unscented Kalman filter. I said x dot was equal to b state vector. It was q dot 1, q dot 2, up to q dot 12. Yes. And I said q dot 1 is equal to q4, sorry, q5, q6. Yes. And I wrote q dot 4 based on the first equation. I call it f1x, f1q, f2q, and f3 based on q. And for the rest, for the stiffness and damping value, all of them are 0, which will be a 0 vector with size of 6 by 1. Yes? Then we have a function here for transition function, which I call it M, the matrix M, which is continuous and is a function of Q and U. And AG, I call it AG here. Okay? This MC is the transition function in a continuous domain, and we need to convert it into the discrete domain. As I said, you can use different techniques like Euler method, Runge-Kutta, or any technique. The technique I used in this example, and I'm going to show you the results based on that, we call it Hans method, or a two-stage predictor corrector method, time integrator technique, actually we call it. And if we have this MC, which we calculated already, the Hans method, I'm going to write it here for you. It says you calculate one x star at time k plus 1, which is equal to xk, which is your state vector, plus delta t times mc. And this mc is this function. Yes. What you do, you write your state vector plus delta t times mc, which is the transition function in continuous domain. And what you do in the next step is you say x hat k plus 1, which is your predicted state at time k plus 1, will be equal to xk plus delta t divided by 2 here for MC, you calculate it based on xk or cube xk. Then you mean xk here, I mean the state vector at previous time step. Then here will be a delta t over divided by 2 MC at xk plus MC that at x star at time k plus. Yes, this is the technique I used to discretize my transition function and use it in Unscented Kalman Filter to propagate the sigma points and predict the states, the mean of the states, and variance matrix of the states. Then after that, I need to discretize my measurement function. And as you know, the measurement function, there is no difference. The measurement function in discrete domain and continuous domain are the same. Then right now, we have everything we need to implement the Unscented Kalman Filter and see the results. Here, for this 3-story building, we were able to estimate the displacement of vibration for each floor and the velocity of vibration. Also, we were able to catch the ground truth for a stiffness value. For example, as you see, I assumed the ground truth for a stiffness value is 40,000, and I started with 30,000. And you see, Unscented Kalman Filter was able to catch the ground truth. And for damping values, I started with the initial value of 200, and you see the mean value of the estimated, the identified damping value. And you see the Unscented Kalman Filter was able to get to catch the ground truth for damping value as well, assuming we don't know the measurement in the second floor. I'm going to ask you something. If, for example, in this simulation, I have used the Hans method to discretize my transition function. I'm going to challenge you and ask you to use Euler technique to see if the results will change or not. What I'm going to tell you, if you use Euler technique, Euler method to discretize the measurement, the transition function, you will not be able to estimate the right value for damping, and it overestimates the damping value, because Euler techniques tends to damp the vibration soon and overestimate the damping value. Then you see that how in this video, in this video, my goal was to show you how can we use the Unscented Kalman Filter to estimate the states and parameter of a 3-degree of freedom system. The reason I chose this case study because I'm going to use it as a benchmark in future videos and try to test other capabilities of the Unscented Kalman Filter. For example, right now here we were able to estimate the stiffness value in 5 seconds. What if there's a change in the stiffness value, which represent a damage in the building? For example, you excite this building with earthquake. At some point, there will be a crack in this first or second or third floor, and the stiffness value decreases. Then, in that case, is the Unscented Kalman Filter able to catch the change or quantify the level of the change or not for us? I'm going to test such a thing using the same case study in the future video, which we talk about it. Thank you.